Begin. It happened.
Huzzah.
Huzzah. Now becomes the part where someone has to tell us, someone has to acknowledge our existence. And by doing so, some kind of quantum thing makes us
You bring
appear.
us, yeah, you make us coherent,
Mm-hmm.
collapse
You collapse our
from
wave
our
function.
our entangled wave function, and no matter what, you're gonna end up with a bald guy.
No matter, whichever way,
I'm not
this
saying which
the
is which.
whichever way the particles, collapse, you end up with a bald guy with the with some facial hair.
Some scruff.
Hey everyone, welcome to live QA with my good friend, sometimes traveling companion,
That's a lie.
Dr. Paul Sutter. So,
It's me.
so do we? Shall we just drop the mat from here on out? It's just Dr. Paul Sutter,
Yeah,
Dr.
yeah,
Sutter,
it's
Dr.
cool.
Paul. That's what Skylius calls you, Dr. Paul.
So Sky calls me Dr. Paul. Some people just call me the spaceman.
Yeah,
Some people call me Dr. Sutter. Some people call me Paul. You
Spaceman.
can call me, uh, yeah, as soon as that was one of the first comments I got because I never watched 30 Rock.
Yep.
So I named the podcast Ask a Spaceman. And one of the first things my colleagues said to me was, "Oh, Ask a Spaceman."
You're
And I
like,
said, What? What?
yeah, yeah. It's an obscure reference to a TV show, and
And I have to live with it forever now.
well, at least it's like you're not given the same name as a major character in a beloved uh, sitcom from the 80s and 90s.
Oh, that's right.
Yeah. And the hilarious thing is, I was talking with, uh, uh, who was it? Oh, the people who clean our house. And she was saying, I was saying, we're making a joke about my name. And she was like, I don't get it. What's the joke about your name? And I'm like, have you not seen the show Fraser? No. So we're
No,
actually moving to a point now where people have no reference
unless they reboot it.
for my name. Yeah. Oh, I guess now that Roseanne's off the air, they may have room to do it.
Yeah. And Kelsey Grammer, as far as I
I
know, is
sent Kelsey
racist.
Grammer an tweet and I said, "Can I have my name back now, please?" Because I had it first.
And what did he say?
He
He
saw
didn't
he hit
respond.
yeah. He just let me eat static.
Now you're blocked by Kelsey Grammer.
Right, exactly. Yeah. All right. So if you have no idea what it is that you've stumbled into, this is my Monday open Q&A where I sometimes just do this solo, sometimes bring a special guest, and we just answer your questions of different specialties. So last week we had Eric Berger from Ars Technica, and he's your spaceflight guy. This week we got Dr. Sutter, and he's going to be your cosmology physics guy. And if you don't have questions for Paul, I got a couple of doozies, which we
I
can.
bet you do. You always save the hardest ones for me.
Well, have you? You know what? We're just gonna. You know what? Let's just go right into it. Maybe you haven't been on top of this, but have you heard that they've maybe detected sterile neutrinos?
No, they haven't.
Shall I hit you with the link? Do you
Yeah,
need?
yeah, yeah. I'll search it. I'm sure I'll just a major physics experiment just detected a particle that shouldn't exist. Oh boy.
Hey, while you're
I
doing that, while you're
assume.
getting yourself up to
Yeah.
speed, I'm to wish Nancy happy birthday. Happy birthday, Nancy.
Oh, happy birthday.
So he's just like he does this. He's just digesting, just taking this new piece of information into everything else he knows, and let's do it.
Okay, so Sabine Hostenfelder is excited by it.
Well, that's good enough for us, isn't it?
I'm reading through it. Okay.
While we do this, Steve Sharmer asks, so when do you predict there will be a coronagraph advanced enough to get an image of an extrasolar planet? So there's actually sort of two ways this is going to go. One, okay, so for people who don't know what a coronagraph is, that is essentially a sunshade, a way that you block the light from the star so that the fainter planets nearby are going to be able to show up. And uh, there are various coronagraphs that have been in the works, and one was just implemented, or is in the process of being implemented for the European Southern Observatory, one of their ground based telescopes. And it's going to be able to show planets next to stars. The next sort of major version of this is going to be what's called the star shade, and that's going to be one of these, looks like a great big flower petal in space, and it hovers about 10,000 kilometers away from the telescope and sort of blocks the light from the star and allows the various planets that are surrounding it to be visible. And so in the next decadal survey, this is the sort of the next version of, and I'm actually working on a video about this right now, but every 10 years, NASA is sort of asks the scientific community for their priorities. They come back with all their priorities. And one of the priorities that people are putting into some of the missions and for the next decadal survey is that the space telescopes be starshade ready. So, which means that, the starshade may or may not get launched, but the telescopes have to be able to deal with being equipped with this starshade and be able to observe properly and be able to use the starshade as an instrument to help them identify planets. So W first is one of them that's going to be that's going to be have to be starshade ready, and you're probably going to see James Webb doing the same thing. And then there's these four telescopes that NASA is sort of juggling right now. LUVOIR is one that we've talked about, and there's three others. And I'm working on a video right now about that. So stay tuned, and I will talk about the starshade readiness and all of this.
So anytime there's, and I was not paying attention to a single word you
Just
said. I was just waiting for a pause,
are
a
you
breath.
starshade ready?
Oh, always.
Yeah.
Yeah.
All right.
Mount it on me and I'll go hunt some exoplanets.
Find some planets. You can see Earth.
So we always have to be careful when there are big announcements, especially big announcements based on a single result that has incredibly far-reaching implications. And this is such a case where we have one instrument, one experiment, and I'm assuming, and this is a large collaboration, they've been running these kinds of experiments for a very long time, that they did a good job, that they understood they understand their instrument, they understand the analysis, the statistics and everything, and they understand the physics, and they put out a good faith paper. And in this particular paper, there is they claim up to 6 sigma detection of a new kind of neutrino, a hypothesis kind of neutrino called a sterile neutrino that would not ever interact with normal matter. But you can catch it kind of in the act, and I can get into the physics if you want. But I want to talk about the thing I always gravitate towards is the significance, that stated number of, oh, this is a 6 sigma detection. This is Nobel Prize worthy. It's 6 sigma if you've properly understood your uncertainties. If you properly and totally 100% understand all of your statistical errors, your systematic errors, how the instrument, how your apparatus actually responds in the real world versus some idealized scenario. If all that's true, then yeah, 6 sigma is a solid detection. But more likely than not, those you did not estimate your uncertainties correctly.
And I think
That's
they'd
where,
hit 4
yeah.
sigma is what I've read.
I saw 4 sigma. I saw another number that said 6 sigma combined, where if you take one detection that has 4 sigma away and another 2, you can add it together. That's not quite accurate, but
Is that how that works? You just add your
yeah,
sigmas together. You have a 2
You
sigma result and
can
a 4 sigma,
if
then you've got a
you're
6 sigma.
measuring if you have two differences and they each carry their error bars, you can measure the number of error bars away from each other those measurements are. But I'll leave that to the side. Um, if and that's where all the nuance and subtlety in modern high energy physics and cosmology is in studying the error bars. That's where the real meat of the discussion is, and where all the hard work and sweat goes is in, are the error bars this big? Are they this big? Are they lopsided? Are they really representing the underlying data? Blah, 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 blah. All these super complicated questions.
Yeah.
And when there's a result that's surprising with a high statistical significance, it could be that watershed moment where we open up our eyes and we realize that new physics is upon us, or the experimenters didn't understand their instrument as well as they thought they did. Especially in this case, when a lot of other experiments disfavor the existence of sterile neutrinos. This idea has been tossed around for decades. Up until this point, we've had no good reason to suspect that sterile neutrinos exist. Now this experiment comes into the mix. Now we got to think a little bit like, okay, are sterile neutrinos maybe a thing? Then we have to explain these other observations that counted against it, or did they do something wrong?
But I mean, just up until last week, we had been talking about the results that have come back from the Large Hadron Collider, and that it has been perfectly, boringly filling in all the pieces of the standard model. Nothing new, nothing surprising. What are the implications if sterile neutrinos are in fact discovered? Like, are we talking Nobel Prize if this is a true thing?
Yes.
Yeah.
Sterile neutrinos, maybe a Nobel Prize, either just for the discoverers, maybe the theorists that invented it, maybe both. That sometimes happens. Neutrinos themselves, a lot of the properties of neutrinos already exist outside of the standard model of particle physics, like the fact that neutrinos have mass. That is not a part of our standard, of the standard model. And if you add in a new flavor, a new kind of neutrino, this disturbs a lot of the fundamental symmetries in the mathematics in nature that the standard model is built on. Like you'd imagine this, the standard model is this perfectly symmetrical castle that stretches far into the sky. And then this is just like a piece of dynamite in one corner that forces us to really reconsider our approaches to the standard model, of views of the implications of the standard model, of we know the standard model is incomplete. We don't really know how to extend it. This could be a window into extending it, revamping it, finding a more fundamental law of nature.
But it's like the first particle potentially that's found that is beyond the standard model, and by doing so requires new laws of physics and understanding to go further. And as you said,
exactly.
This is Nobel Prize.
I would say this is Nobel Prize if it's right. I'm not really gonna feel so strongly that it's right. Like, it's just because it's just one paper. And even though these researchers are great, and I don't even know them, but I'm sure I respect them, and they did a good job at everything. It's just one result. We're gonna need some more thinking about this.
Right. Yep.
So I just tend not to get too excited.
Yeah, no, I absolutely. Results. But I guess, with the caliber of the people who are excited about the result by the way they put the paper out into the community, they're doing all the right things, and it would be a pretty amazing discovery to actually have this. So
yes, they're doing science right. Like they're publishing their results and their methods. They're opening it up and say, okay, now what, everyone?
Yeah. Tear it apart, please. So go ahead. If you've got any questions for Paul, people are asking sort of your credentials. Can you give just a quick explanation of where you got your science from?
Oh, I make it up all
Right.
the time. But what I've done is I've read a bunch of Wikipedia articles, so I know all the jargon, but I
Right.
really have no idea what I'm saying.
Right. Yeah. So there you
Yeah,
go.
no clue. I got my bachelor's in physics in from California Polytechnic State University back in the day in 2005. Went on for a PhD in physics from the University of Illinois at Urbana-Champaign as a Department of Energy Computational Science graduate fellow, and finished that in 2011. Went on to the Paris Institute of Astrophysics, or Institut d'Astrophysique de Paris, and spent 3 years there as a postdoc, then 2 years in Italy at the Astronomical Observatory in Trieste. And now I am at The Ohio State University with the split position where I am half-time at the university and half-time the chief scientist at COSI Science Center, which is the Science Center
There you go.
in Columbus.
And
That's me.
specifically, you did a lot of your work looking at cosmic voids. A
Yeah,
lot of
especially in my
nothing.
postdoc work. Yeah, for sure. So my graduate work, I was doing computer simulations, big, heavy duty, giant simulation stuff of 100,000 processor kind of runs, looking at magnetized outflows and clusters of galaxies, their relationship to quasars and black holes and all that. I pivoted after grad school because I was really tired of that stuff. Worked on large scale structure, cosmology, Big Bang. I was a member of the Planck collaboration doing data analysis of the cosmic microwave background, working on cosmic voids, the large empty places in the universe, doing data analysis problems for its finding the first stars for radio interferometry. And I continue some of those research lines today. In fact, this week I have a collaborator visiting me all about voids.
Excellent. It's an interesting question. So Steve Sharmer asks, will the Chinese share the information they get from the radio telescope on the far side of the moon? Have you been following this mission at all?
A little bit. So it's not, is it, it's not like going to land on the far side of the moon. It's just going to be in orbit, right?
Well, they're sending a rover. So
Mm.
they've put a spacecraft to the Lagrange point, to the Earth Moon L2 Lagrange
Yep.
point, and it's going to be acting as a relay for communicating information from the lander rover that they're going to be putting on the far side of the moon. So the purpose of this is to act as a relay because we have
Mm-hmm.
no communicators on the far side of
Yeah.
the moon, and that's its main purpose. Will China be contributing the science to it? I mean, they're actually pretty active on Astro PH. I see a lot of papers
Oh,
from
yeah.
Chinese scientists. They've got the FAST telescope, which is the largest radio telescope in the world,
Mhm.
single radio
That's
telescope.
right.
They're building
Interferometers are bigger, but
they're
yeah.
building the largest steerable dish telescope, like like a big version of the Jodrell Bank, and and other people can do research time on their projects. So I can't imagine why they wouldn't be sharing their scientific data with the rest
Yeah,
of the
like
world,
any
especially if they found something
major
cool.
installation is probably going to be a mix of there's initial funders and initial backers, initial collaborators. They'll get first crack at the instrument. They for it as a reward for doing all the hard work of actually designing it, building it, testing it, operating it, working out all the kinks. They get exclusive access to it for a set period of time, and then it'll probably open up to the community for competitive proposals if it's that kind of instrument, or it might just stay inside the collaboration depending
Yeah.
on the funding structure of it.
The tough part with stuff that comes out of China is that it's in Chinese. A lot of the news releases, a lot of the sort of
Mhm.
official documents and stuff that you try to get, it's all in Chinese, and so we don't learn as much here in the West about the projects, about their discoveries, about the new missions that are
Yeah.
coming up. There are a few a few outlets like I like Spaceflight Now and America Space. Ironically, does a good job of they publish a lot of good stuff on Chinese launches and things like that. But a lot of it's just
Mhm.
sort of you find out after the fact. But with
Yeah.
the lander, we're actually we're seeing quite a lot of information. They've been sort of telegraphing what they're going to be doing and then upcoming missions. So
Yeah, we saw that a lot during the Cold War of Soviet scientists having very very limited access to the West and vice versa, and so they you would now decades later you can see these parallel trains of thought where there were Soviet scientists and Western scientists both coming to the same conclusions, and
Right.
they get to meet like once every 5 years or something ridiculous, and they would meet and they say, "Oh wow, turns out we both figured this
Yeah.
out."
Yeah. Yeah.
Um, and it turns out the Soviet scientists didn't get sufficient credit for their work just because it wasn't a part of the Western
Yeah.
journal tradition. And I think we're seeing that with Chinese scientists. So a lot of young Chinese scientists will come to the U.S. for graduate school, for postdocs. They'll come to Europe too. They'll spend some time here learning from the best, which is great, and then head back to become a professor at a university in China. And then, for all intents and purposes, they drop off. They don't publish in English. They don't attend the major European or American conferences. And so sometimes you find out what Chinese scientists are doing, and it's super cool. Sometimes they're part of collaborations, but I think we're missing a lot.
And Astro YYZ is noting the Chinese are looking for science partners from other UN nations for their as of yet unbuilt new space station. So I don't know if you've seen that as
Nice.
well. They're working on a space station. They're looking for partners to come on board with that because the Chinese aren't allowed to contribute with the International Space Station, and so they're building their own station and they're
Yeah.
bringing on other partners who maybe haven't been able to get involved on the International Space Station. So
Staying busy.
yeah, yeah. I think that's I mean, as we've seen with their human space exploration efforts, I mean, it's kind of amazing how quickly they've gotten, and that's sort of one of
Yeah.
the advantages you can have from a fairly centralized system is they can just make these kinds of goals and directions and just implement them, and they're not that concerned with having to
Be
convince
safe.
yeah, or convince the populace or convince the other parts of the government. They just do it. So, which
Well, I
has
would
all
say
kinds of downsides. Like I
I
think it's
think
really
that's
important to say there's all kinds of downsides with that
and
sort of,
I think
you
that's a
know,
pretty broad brush there,
yeah,
even in centralized governments, even with pure autocratic governments, there's a lot of interests that need to be appeased in order to push your policy through. Just because there's one person at the top doesn't mean politics goes away. Uh, what I think we're seeing is it's not necessarily that the government just decides this and it's just happening, is that a space mission or space missions or a space agenda aligns with the priorities of the ruling parties and the people that the ruling parties have to answer to.
yeah. So go ahead, hit us with some questions. Why Orgahedan wants to know why can't the Chinese contribute to ISS? This is like some international treaty from the United States, right? It's like a security requirement. While the
Yeah, I think
Russians
so.
help build it and they supply astronauts to it, and so they're part of it. And in fact, the Russians have come on board to help build the Deep Space Gateway, so they're going to be a part of it as well.
Mm-hmm. If that will ever happen.
Let me see. This is an interesting one. R. Jones says like boosters possibly landing near your house. Yeah, that's the kind of thing, right? Where boosters come crashing down in the near your house, and it's
Mm-hmm.
just one of the sort of prices that people have to pay for their country building its ability in space exploration.
Yeah.
Flip Flops asks, concerning gravitational waves, do all objects which interact with each other create microgravitational waves, or is space time too tough for it? So, does
Yes.
everything moving create gravitational waves?
Yes, basically.
Just
Yeah.
little ones.
Waves upon waves upon waves upon waves.
So, we are experiencing the gravitational waves from every single moving object within our light cone.
Yes, so there are yes, with within our cosmological horizon, there are, if you remember that
Yeah,
fun
yeah. We
episode,
just did an episode on cosmological horizons.
there are gravitational waves sloshing over us right now that are left over from the event of inflation 13.77 billion years ago.
And that's actually one of the sort of the next missions. The Lisa mission, the Lisa Pathfinder went to test the technology of Lisa. Following that is going to be the actual Lisa mission, and then
Mhm.
following that, we hope is going to be the Big Bang Observer
Yep.
satellite, and that is going to be able to, we hope, see the gravitational waves from that inflation. What do you
Yep.
think they would look like? What would do you think they would tell you?
Wibbly wobbly,
Wibbly wobbly, timey wimey.
wavy, davy.
Yeah.
We honestly don't know. I mean, we have a really solid idea of what inflation looks like, but we don't know the particulars. And the physics that generates and drives the inflation is still really unknown. So it would imprint itself, the gravitational waves, it would have a very, very peculiar spectrum where it's very, very hard to put into words. So I'm going to avoid it. But it would look very distinct,
Right.
and it we've run models, so we have all the templates. We know of various inflation theories what what the gravitational wave signature would look like.
All right.
It
Here's
wouldn't look like the merging black hole thing with a
right. So you would see a different
wouldn't.
wavelength, and it would instantly, like, if you could, get a time machine, bring those inflationary gravitational waves back and hand them over to some cosmologists working on this, they would go, okay, that perfectly explains this theory and throws out all those other theories, and
Yes,
it would
it
be
would
a
constrain, it'd be a window into the inflation event
yeah.
itself, which was all the excitement of BICEP. Remember that a few
Right.
years ago, which was what, a 4 sigma detection, except whoops, they forgot, they screwed up their dust model,
Yeah.
which is a perfect example of, yeah, I believe you're 4 sigma if you did everything right. If you screwed something up, all your uncertainties screw up too. That was the imprint of gravitational waves on the cosmic microwave background, shifting the light pattern in a very subtle way.
All right. I had one question, then I'll get to George's question as well, but I like this one here. So, um, where was it? Okay, so this comes from Crush Not. Dr. Paul, any thoughts on quantum immortality, aka many worlds interpretation of Schrodinger's cat, where you, the observer, is the cat, and you can only observe worlds where you exist to observe?
Yeah, you're willing to give it a shot. I'm not going to participate in that particular experiment.
Right.
So physics is a series of bets on how the universe works. That's a bet I'm not willing to take.
So George Lancaster asks, can the underlying expansion of the universe cause matter in two relative frames to go faster than the speed of light and cause causality issues?
Yes, objects at the distant edges of the universe are receding away from us faster than the speed of light. And it means it doesn't cause a causality issue, but it does mean we will never, ever, ever, ever catch up with them. Ever.
Right. Which, so I dealt with this as a question in the question show this week that I just shot, and someone was saying, so even though we may live in an infinite universe, for all practical purposes, it's a finite universe,
It's
and
our bubble.
getting more finite every day.
Yes. So even though the universe is expanding, our observable patch shrinks with time.
Is the density of that observable patch going down as well as material is sort
Yes.
of falling over that cosmic horizon?
Yes, exactly. The matter density of the universe continues to drop, but the dark energy density remains constant. That's its superpower. That's its special thing. The density of dark energy stays constant. That's what drives accelerated expansion. So as the universe expands, the matter density drops and the total amount of matter stays fixed. And in a larger volume, density drops. But dark energy, the density is constant. So as the universe expands, you get more and more dark energy.
Right. And so eventually, well, I guess eventually the universe will be almost all dark energy,
Mhm.
except for whatever dark matter and matter hung out in one big blob.
Yes, in what will become the merged remnant of the Milky Way, Andromeda Triangle, and the entire local group will stay bound together, with everything else carried away outside of our event horizon, outside of our future light cone. So we'll fade from view. And then dark energy will be so strong at that point that if you just jump away from that local group, if you take one little hop away, the accelerated expansion of the universe will just flick you right away.
And that's assuming that dark energy is going to remain constant. If it
Yes,
increases,
yes.
then it's a whole other problem.
A whole other problem. It might decrease, it might increase, it might shift around, it might transform itself into new matter fields like inflation did. Who knows?
Who can say?
It's not sterile neutrinos, though.
All
That's
right,
the end. I can
here's a
tell you
good
that.
one. Lost and Boundless asks, and use the question mark. Thank you. When two black holes begin to collide at a fundamental level, what is happening as one begins to spaghettify? Are they even spaghettifying?
They do distort. The event horizons of the black holes do distort. So as they get close, instead of being perfect spheres, they extend and they kiss at a little point, and then it looks like a dumbbell shape, and then the dumbbell gets bigger, and then they're a lumpy, lopsided black hole rapidly rotating, and then it settles down into a sphere and it vibrates, it releases some extra amount of energy, and eventually settles down to a single sphere.
But what's going on inside those event horizons, we can never know.
It's what's going on. Well, we can know because we have mathematics and we have general relativity and we have quantum field theory, so we can make some pretty solid statements about what happens inside of the event horizon.
Mm-hmm.
We can't visit it and
Right.
tell everyone else.
How romantic. Adorable, invisible destruction.
Mhm.
So Liberty
I did see a
309.
question.
Oh, you
Oh,
got
go
one that
ahead.
you want to take on?
I saw there was a question they asked a couple times by Cat Soar. Can you explain what type of data is being collected by the Event Horizon Telescope effort to get a photo of Sagittarius A star? So, Event Horizon Telescope is a radio telescope, and specifically a radio interferometer, which means it's multiple radio antennas scattered all around the world, all trained on the same target, collecting the exact same data at the exact same time. And then we all collect it together into one giant radio picture. So it will be a picture, an image in the radio spectrum of the black hole itself and its accretion disk, assuming they don't screw it up.
Mm-hmm. What I've heard is that we're going to see it in spring of 2019.
Spring of 19. So they've already pushed it back because I
Yeah.
was here in fall
Yeah.
of this year.
Yeah.
But yeah, this is super tricky data analysis. And radio astronomy is kind of a black magic kind of thing in astronomy where you have to do special spells and incantations and certain numbers of sacrifices of graduate students before you get out a reasonable result.
I mean, isn't the trick with this is that with radio waves, it's just barely feasible to take all of these readings with all these different telescopes and merge them after the fact and turn it into one big picture. You can't do that with any other wavelength beyond radio waves. So
You can do it with other wavelengths, but it's exceedingly
after the
difficult.
fact,
After the fact,
okay,
yes.
okay,
There are extra terms in the mathematics that make it very, very difficult. So difficult that it's rarely done,
right,
but it can be done.
yeah. And so it's not like, I mean, wouldn't it be wonderful if you could just take all the world's observatories as well as the Hubble Space Telescope all point at some object and and gather a bunch of light and then take all that and turn it into a telescope the size of the Earth.
Mm-hmm.
All you get right now is the total, I guess, surface area of all those telescopes, which is not a telescope the size of
Right.
the Earth. But
Right.
with the Event Horizon Telescope, that's what they're doing.
And this is the magic of radio
Right.
interferometry.
Well, all interferometry, but radio being the one again that is feasible to do after the fact.
It's the easiest to do.
Yeah.
Yeah. So you can make this is what powers almost all major new radio arrays. And the best part is the arrays themselves are dumb. They're like coat hangers, right? Or they're just like super chicken wire dishes. It's just like you just need to detect radio waves and
Right.
you just need a hunk of metal to do it. All the hard work gets done on a computer later on.
Yeah. So there you go. Avy Scott and Flower 20. I've heard 2019, but I promise you, every time I talk to any one of these people, I just nag them. How about now? Can I see it now? Can we get the
How
picture
about now?
now?
How about now?
But you've sort of tried to prepare. We've tried to prepare people emotionally for what they're about to see when they do see
It's
that
going to be a
picture.
fuzzy blob.
A fuzzy blob.
But hey, it's the best picture of a black hole we've ever had.
Yeah. So okay, so a bunch of people are asking about this. How can things expand, move away faster than the speed of light?
Okay.
Do you want to take a crack at that?
Because why not?
Yeah. Now I got
Were
slapped on the
you,
wrist by
were
Sean
you,
Carroll when we first met.
yeah, well, yeah, I
You,
remember
yeah,
that.
you helped me through a very dark time when I was saying this, and Sean Carroll came down on me. So
So I remember you were right. You were fine. Sean Carroll was also right and also fine. There wasn't necessarily a reason to come down hard on you because like in most things in physics, there's multiple ways to look at a single problem. You can look at it with different lenses, different sides of the equations, different combinations of jargon. What matters is the mathematics, right? That's what we really care about. But we're on an abstract level where we're using words in extra hand gestures to explain what's going on with mathematics. And whenever you do that, like any translation, some translations might fit the mood better than others. And it's a game. And so things at the far edge of the universe. One way to say it is that, yeah, they're receding faster than the speed of light. Special relativity is only a law that applies to your local region of space. It can't tell you about things that are things that are really, really far away. They can have whatever speed they want. It doesn't matter. And that's totally fine and legit. And I think that was the approach you took. Sean Carroll's approach was that for objects far away, there is no such thing as velocity. Velocity, that word velocity, can only be applied to things that are really close. So to me, it's six of one, half dozen of the other, because special relativity talks about velocities in your local region of space. Away from that bubble, either special relativity doesn't care because it's outside of its domain, or the word velocity is undefined, which means special relativity doesn't care because it only cares about velocities. So there you go. In the common astronomy parlance, the day-to-day operations, they'll refer to recession velocities. They'll tag a galaxy and they'll put a speed on it in kilometers per second. And that's just the way it's been done for 100 years. Whether that has any physical meaning or not doesn't really matter. Just whatever.
Uncle Bill Drew, and you sound exactly like me. He's saying in the comments, "Can I see it now? Can I see the picture now? What about now? Can I see it now?" That's pretty much that's anyone in that community. When I talk to them, I say, "And by the way, can I see a sneak preview of the picture from the Event Horizon Telescope?" Nobody has been willing to show it to me.
Yeah, just take a picture of this live stream, put a big take some petroleum jelly and smear it on your screen, and that's about what you're
That's
gonna
about
get.
what you're going to see. Yeah. Pixar didn't happen. All right. Go ahead. Hit us with some more questions. And use the little question mark if you want to get our attention.
Was
But
there a special question mark emoji thing?
but so just to kind of hash this out one more time, because the right now where there are these galaxies that are moving theoretically faster than the speed of light, or not
Observationally, they are.
observationally moving faster than the speed of light. What about that time during the period of inflation where the universe doubled and doubled and doubled and doubled in size a bunch of times in a fraction of a second?
Great times.
Great, good times. It
Wow.
had grown quickly.
Mm-hmm.
Some might say that it had moved faster than the speed of light observationally. From
Yeah.
parts were moving away from each other at very rapid
Superluminally.
super. Oh, okay, there you go. Superluminally. Yeah.
Uh, Parts of the universe. If you live in an expanding universe, no matter the rate of expansion, the there will be parts of it that are accelerated, that are moving away from you faster than the speed of light. If the universe isn't expanding very quickly, super slow mo snail's pace, then you have to go out really, 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 really far till you reach that
Right.
point that's going fast. If the expansion is really fast, like during the inflationary epoch,
Then you didn't have
then
to go
it's
very
like
far.
your next door neighbor is recedes away from you faster than the speed of light. Right now, we're kind of in between.
And it's going to get right worse in the future as dark energy continues to
Yes.
take over,
Yes.
which is this really weird thought to think about the far, far future where what would have been an observable universe, our observable universe, there will be these regions that are vastly bigger that have nothing in them, just dark energy accelerating the expansion.
Mm-hmm. Mm-hmm.
Hmm. Ooh. All right. Neil, I'm sure you've had this one a million times. But Paul, what do you think of Verlin's gravity ideas?
Okay. Like, interesting line of thought,
Yep.
intriguing based on these very, very thin threads that we've been picking up over the past few decades about the nature of black holes and the connection between gravity and thermodynamics. Like, I can see that thread. It's so thin. It is like no thicker than a hair on my head,
Mm-hmm.
which is very thin. And but there is a thread there. That said, he's been working on it for like what, 2 decades, and at some point we gotta say, like, okay, maybe that's the wrong line of thinking.
Right. Crushnut says, Dr. Paul, your video about cosmic rays and how we have no idea where high energy ones come from blew my mind. Who's looking for the source, and what is your thoughts on where they come from?
Ooh, who's looking for the source? So we have a lot of high energy cosmic ray detectors. Even the ice cube that announced this potential neutrino result, they're all cosmic ray detector. They're searching for high energy cosmic rays. There's instruments called Hawk in Mexico and Veritas in let's put it in Southern California, if I remember right. There's Pierre Auger Observatory in Chile, who knows? Like, I'm just picking random countries out of a hat. And so there's worldwide efforts to look for ultra high energy cosmic rays. There's the Fermi Large Area Telescope, the Gamma Ray Observatory. Um, there's many collaborations, dozens, I'd say, all around the world, from small to big, looking for cosmic rays of all kinds, especially the high energy ones. Where they're coming from, I have no idea.
So, I mean, just to give people a sense of what these cosmic rays are, I mean, these are these high energy particles that are arriving with levels of energy that we couldn't possibly generate in the Large Hadron Collider, right? Like, they are off the charts
They're
powerful.
beastly.
Yeah.
Yes.
Uh, Tera electron volts.
Something crazy
Yeah.
like that. I know I just did the podcast on it, but
Yeah.
as soon
Well,
as I
that's
recorded
the
it, I forgot all the
yeah,
details.
that's the easiest way to completely forget any information on a subject is to do an episode
Just
on
to
it.
teach it.
Yeah. But what are some
Yeah.
possible ones? Like it's got to be like the biggest machines in the universe, right? We're talking
Yeah, so
supermassive
active
black
black,
holes,
yeah.
colliding objects.
So even colliding objects don't seem to be powerful enough because the energetics don't line up in the right way to accelerate these kinds of particles. You need raw energy, plus you need the physical conditions that can spin up a particle like this to such a crazy
Hmm.
velocity and send it blasting off. Active galactic nuclei, quasars, seem to be the most likely candidates because they're enormous wells of energy.
Hmm.
But there's a cosmic distance limit to these high energy cosmic rays. If they travel, because they're traveling so fast, the cosmic microwave background with this bath of low energy photons that we all sit in every day and soak in, when you go that fast, it gets blue shifted up to gamma rays. And they literally start like smacking into you as you're trying to rush that fast, and they slow you down. And so there's a distance limit to how far these ultra high energy cosmic rays can go. And it's something like 5 billion light years, something like that, if I remember right, plus or minus. And there's no supermassive black holes, active quasars in that limit, except for one. And the cosmic rays aren't coming from that, they're coming from all over the sky. So that's the big mystery of the most obvious culprit has an alibi.
Which is relatively nearby active quasars. They don't seem to be the cause.
Right, or because there are no active quasars nearby.
Right. And like and there are pretty much no more powerful machines in the universe than those. I mean, maybe uh, gamma ray
Maybe gamma ray
bursts.
bursts. Yeah, exactly. Maybe gamma ray bursts, but these don't seem to be timed with gamma ray burst events or sourced from the same part of the sky.
Yeah.
Some line of thinking is maybe has something to do with transients. Maybe there are some quiet black holes nearby, supermassive ones in nearby galaxies that just take
Mm.
a gulp and burp for a couple weeks or a month and then go away. And then they're the source of these energies. But because we don't have dedicated, continuous observing to spot these, we just miss them. That the quiet black holes aren't really that quiet after all. Maybe, I don't know.
Yeah. Philip James asks, so are there elements that we'll never be able to see inside of a black hole, or is it just a particle soup? Back to that old question, what's
What's
inside the event horizon?
what's inside the event horizon is the singularity. All matter inside the event horizon. As soon as you cross that event horizon, you are headed directly for the singularity. You cannot escape it. The singularity is, how should I say this? It's tempting to think of the black hole like a cell with a nucleus and little ribosomes, and proteins floating around, and then like the membrane surrounding it of the event horizon. A black hole, physics is way simpler than biology. A black hole is simpler than a cell. A black hole, by definition, is a singularity and event horizon.
Right.
That's it.
It's
Just two parts.
it's
Just two parts.
it's made of black hole.
Exactly. It's its own thing.
Right. And this is, I mean, we've chatted a bit about this in the past, this idea that if you take a regular matter object and you crash it into an antimatter object, you take a regular matter black hole and you crash it into an antimatter black hole, you're just going to get a black hole with double the mass. You're not going to get and that's because actually it's a trick question. There's no such thing as an antimatter black hole. You could take a black hole's worth of energy, collapse it into a black hole, and it'll turn into a black hole. Take a black
Yep.
hole's worth of matter, black hole's worth of antimatter, crash them together. You just get black hole. It's all just made of black hole.
Yeah, and just two parts, the singularity and the event horizon.
But what?
Really just the singularity.
Right.
The event horizon is a consequence of the singularity.
But we see objects here in space, things like a white dwarf, which is, you've reached this point where
Mhm.
the particles are as munched together as they can, and then you can have one stage smaller with a neutron star where they get even smaller. Maybe there's a quark star, and maybe there's a preon star, maybe there's a couple more layers, and then black hole. And then at that point, it's like, is there some other fundamental shape that we're not aware of inside that singularity, or are we
Yeah, I mean, I
certain that
should say,
it's not?
yeah, I need to preface all this with this is the picture in general relativity,
Yeah,
which is how we predicted that black holes exist. We know for sure that picture is incomplete.
because the laws
Uh,
of physics break.
yeah, even though a black hole is entirely 100% singularity, singularities don't exist.
Yeah.
It's something else, but we don't know what that something else is.
Kreshant is asking whether black holes have hair or not.
Probably not, but maybe yes.
What is?
Active research question.
Yeah. What does that even mean?
Black holes are, in the simple picture of general relativity, insanely simple. Like I said, you can describe it with three numbers: just mass, spin, and charge. You have two black holes with the exact same mass, spin, and charge. You can swap them around. You'll play that cup game or whatever. You couldn't tell them apart. That's what's said to be hairless black holes. And I'm kind of annoyed. I think it was John Wheeler that coined this phrase, because now everyone who imagines like, are black holes hairy, even on like big budget TV shows, they'll show black holes with
With
like
hair.
hairs poking out, like tendrils. Uh,
So it's
what is
just
it?
like that.
Yes, exactly. What am I trying to think of? What's that thing like on a cell, like
Oh,
cilia? Like,
okay. I'm
and
just imagining some eldritch dark god
oh
reaching
yeah,
from,
reaching out
yeah,
from the
reaching out, ya Cthulhu tag, and
wow, yeah. Now you've done it.
that's
Uh,
it. I just summoned it.
it's just happened. Okay.
Yeah.
Uh, a hairy black hole is a black hole that has more information accessible to us about its properties.
A viewer wanted me to do an episode on the no boundary theorem from Hawkins. Hawking.
Okay.
Is that just a finite universe that wraps on itself? What is the no boundary theorem? Let's see what Wikipedia has to say. Because I read it and I was like, oh, that's the. From what I understand, it's a finite universe as opposed to an infinite universe.
It's a little more complicated than that. I'm refreshing my memory.
It's like seven. Maybe I'll have to have an interview with you again. We'll do another
Yeah.
collaboration and we'll talk about the no boundary theorem.
Yeah, let's talk about that, because it's, in one sense you can think of it, yeah, like even in an infinite universe it can be boundless yet finite, um, but has more to do with the early state of the universe rather than its present day's size and extent.
Mike McHugh, are there drugs I can take to make me smarter? I
Yes,
like
the drug
like
of
of
knowledge,
knowledge, of practice.
of learning,
Well,
books.
no, but I mean, I get that question a lot where people say like, "Oh, I'm not good at math, so I can't become an astronomer, or I can't become a physicist." Like, Paul, are you good at math?
Probably not.
Like, were you always like you looked at math problems and they just jumped into your brain and you totally understood them?
No, I actually struggle with basic arithmetic.
Mm-hmm.
No, I math was always one of my hardest subjects. And in my career in physics, especially undergrad and grad school, the pure theory, the pure math classes were always the hardest ones. The analytical analysis and mathematical methods classes, that's where I had the most challenge. Thankfully, I am somewhat gifted and talented with computer programming, and that's how I got into computational science and computational physics and computational astrophysics. Of I am pretty good with mathematics on a computer and making computers do my bidding. And there's a lot of variability of skill sets in the physics and
Hmm.
astronomy and science community where yes, mathematics is a part of it, but it doesn't have to be the whole story. There's a lot of physicists that are great, builders, and they're the ones building and designing and testing radio instruments or the ice cube experiment or the Large Hadron Collider, or operating it or designing it or making sure it's as efficient as possible. There are ones who are really good at data analysis or data collection, and there are ones that are good at pencil and paper math. Really, it's more about thinking rigorously and logically, and that is something that people have varying levels of talent, but it's not an easy thing for anyone. It's a skill that
Yeah,
you
and I guess that's the point, right? Is that none of this stuff is going to jump into your brain immediately and make a ton of sense. It is this step by step practice that you do. And there are plenty of people who never saw themselves as math people or as physics people, but are fascinated by the questions, and so they just toughed through the work to build up the practice. And you spend day after day after day doing equation after equation. I mean, you will build the skills and you will be able to do the math that is required for you to be able to do your job. If you need to
yep.
calculate a fast Fourier transform or linear algebra or Fourier transform, linear algebra, or the various requirements of calculus. Like for you do kind of the same math again and again and again, right? I mean,
Yeah, and as you progress in your career, you specialize. So you become familiar with a certain set of computational toolkits, a certain mathematical set of toolkits that appear quite often in your area of research. You become familiar with the background papers and the logic and the thinking and the essential physics and math behind that, and you specialize and you grow and you practice, and you reach your breaking point, and then that's where you apply yourself.
yeah. And I really am a believer in that. Very, there are people who enjoy it or have an aptitude for it, and that sort of keeps them going through the hard times and the dark times. But for
Which there are a
most
lot of.
people, which there are a lot of in all fields, but for most people, if you are fascinated by space and astronomy, or you're fascinated by computers, or you're fascinated by physics, you can absolutely build up the math skills or the physics skills to be able to do the work. You just have to apply yourself and be willing to. You wear this shirt periodically. You just have to be willing to put in the practice. It's just time. You just throw time at the problem, and you will build the skills. So whenever anyone tells me that they're not smart enough for math or whatever, I'm like, oh, it's not what it's about. We've got like
Not what
2 minutes left, so we need to
Oh no,
shamelessly self promote a couple of things before we
why
wrap
not?
things up. Yeah. First, where can people find her? If they're enjoying this conversation, this is what you get over at Paul's YouTube channel.
Yeah, except I'm by myself
By
most of the
yourself.
time,
Yeah.
and I talk to myself, but I'm pretty entertaining. Yeah, so on my channel I have three sets of videos. I have Ask a Spaceman, which comes out every week, which is 5 to 15 minute long discussions on a particular topic in astronomy and physics and science and all that. I think coming up next week, I'm talking about how rockets work from the perspective of a physicist, which is going to be very, very simple. And I have COSI Science Now. These are 1 minute long videos about the latest science news, just something cool, a fresh perspective on it. And then I also host Space Radio. This is my weekly radio show on WCBE Columbus. We live stream the recording of that show where you can ask questions just like you've done now, except the answers become recorded and broadcast
Whoa.
throughout the country.
Old-timey radio. And then let's also shamelessly self-promote something that we're going to be doing together, which is that we're going to Costa Rica.
That's right. This September, we're going on a cruise together. So sorry, all you suckers who couldn't get on the boat ride, but you have another chance to party down with the two best bald science explainers in the world
In this
in
live
Costa
stream,
Rica.
anyway.
During this live stream located in Ohio
Yeah.
and Vancouver.
Yeah, I think that's safe.
Between the ages approximately 35 to 55.
I think that is safe to sort of, yeah, define it that way. Yeah. So what are the dates? March
It's March.
2019.
I'm pulling it up because
Yeah, I don't remember either. And we did a promo that I'm gonna run.
It's a trip. So if you're interested, if you like to go on trips,
Yeah.
and
Yeah.
you like stargazing and you like cool places and you want science people to hang out with you, to celebrate with you, and to teach and learn you some stuff, March 2nd through the 10th, 2019, it's Costa Rica. It's an all-inclusive trip, including flights down, trips to Guanacaste. So during the day, we're doing like Monteverde Cloud Forest. We're doing zip line tours. We're visiting a volcano, and then every night stargazing with some cool telescopes.
Yeah, we've partnered up with Oceanside Photo and Telescope, and they're going to let us bring a bunch of really cool telescopes with us. So we're going to be setting that up every night. We're going to be teaching you the night sky. We're going to be observing some objects that you normally can't see from the more northern regions like where we are, like things like the Omega Cluster, even the Magellanic Clouds, I think are kind of visible from that perspective. So I'm really looking forward to that, and the skies are going to be dark. So if Costa Rica is a place you kind of want to go, you should totally look into it. Go to Astro Tours.
And if you've never thought of it, astrotours.co/Costa Rica. If you've never thought of it, go to the page. astrotours.co/Costa Rica. Get your name in. It's just $500 a person to deposit. So if you're kind of waffling, if you're kind of on the fence, go down, register, put in the deposit, get your name on the list. You have time to get your money back if you decide not to go on the trip. But get your name in to reserve your spot.
Yeah. Awesome. Well, Paul, thank you so much for taking the time to answer everyone's questions. A big thank you to all of the people who watched us today, and to all the people who are moderating. A big thank you to Nancy Graziano, who configured Nightbot to say all these things that it's doing right now. So there's tons of information in there. No plans for who the guest is going to be next week. Give me some recommendations if there's someone you want to see me talk to next week.
Paul Sutter.
Again?
Yeah, why not?
Sure.
Hey, I'm on Sky's channel.
I know, once a week. Yeah. So, you're welcome back anytime, man. But
except for most times.
Except anytime. We will drop everything and do a live stream at your any whim, Paul.
Wow. Yeah. Now that's power.
That's power, exactly.
I'll see you in 8 hours.
All right, everybody. We'll see you next week.
Take it easy. Thank you, everyone. Great question.
On Wednesday, for the Weekly Space Hangout, if you want to.
Yeah, there's that too.
Continue. I'm sure at that point you'll be much more knowledgeable about stale neutrinos. All right.
If you insist.